Hello students, today we are going to discuss the statistical hypothesis testing for comparison of two population means mu1 and mu2 respectively when the two populations are independent of one another. We will discuss the two sample z-test and the two sample t-test. Please once again remember the complete test IDs. They are the two sample z-test, not just z-test, and the two sample t-test, not just the t-test. In fact, the students are required to know the z-test, the t-test, and also the paired t-test in order to understand the two sample z-test and the two sample t-test, which we will discuss today. Let me repeat. The two sample z-test and the two sample t-test are the test procedures reserved for two independent populations. By this point, you must know when to use the two sample z-test and the two sample t-test. As always is the case with all the z-test procedures, the two sample z-test requires that sigma 1 and sigma 2, the population standard deviations for both independent populations, to be known. As always is the case with all the t-test procedures, the two sample t-test is used when the two independent populations have unknown standard deviations. In that case, we will use the sample standard deviations S1 and S2. Remembering the complete test IDs and knowing when to use each test procedure will be extremely helpful for the exams and also for your any other academic and research projects. All right, I hope this part is clear. Let's first look at how to write down the null and the alternative hypothesis for comparison of two means between two independent populations. We will first let mu1 and mu2 be the true means of populations 1 and 2 respectively. Comparison between two population means can be given in two forms. Let me call the first one the basic form. What I mean by the basic form is direct comparison of two means to decide if one mean is lesser than, not equal to, or greater than the other mean. We can write down the null and the alternative hypothesis this way. The null hypothesis H0 will be of the form mu1 equals mu2. The alternative hypothesis will decide whether the test is left-sided, two-sided, or right-sided. For a left-sided alternative, mu1 should be lesser than mu2. For a two-sided alternative, mu1 should be not equal to mu2. For a right-sided alternative, mu1 should be greater than mu2. Before writing down the null and the alternative hypothesis, it's required to define mu1 and mu2 in the context of the problem given. You must use the given population names and label which population means should be mu1 and mu2 respectively. Note that the direction of the test as left-sided or right-sided is completely based on the way you define mu1 and mu2. For one student, a test could be left-sided based on the way he or she defines mu1 and mu2. And for another student, it could be a right-sided test in case if mu1 and mu2 are defined backwards. They both can reach the same correct answer. However, to avoid any confusions, please note that you must first define mu1 and mu2 before writing down the hypothesis. There are points assigned for correctly defining mu1 and mu2 for all two mean comparisons. All right, for the basic form, the null hypothesis H0 can also be seen as mu1 minus mu2 equals 0. In MS Excel, mu1 minus mu2 is called the hypothesized mean difference. So, the null hypothesis in the basic form can also be read as the hypothesized mean difference being equal to 0. We don't use this form of the null hypothesis except for the confidence interval method. The confidence interval for two mean comparison is constructed for the difference between the two means. When your hypotheses are in the basic form, all you have to do with the confidence interval method is to see if 0 is inside of the confidence interval. If it does, then accept the null. Otherwise, reject the null. Well, we can discuss the testing procedures a little bit later. For now, we will see the second form of writing down the null and the alternative hypothesis. All right, the second form is a bit more advanced combination of hypotheses than the basic form. Therefore, I gave it a name, advanced form. In the advanced form, you can compare the mean of one population against the mean of another population plus or minus a certain value. The null and the alternative hypothesis can be written this way. The null hypothesis will be of the form mu1 equals mu2 plus k, where k is a real number. For a left-sided alternative, mu1 should be lesser than mu2 plus k. For a two-sided alternative, mu1 should be not equal to mu2 plus k. And for a right-sided alternative, mu1 should be greater than mu2 plus k. In the advanced form, you can see that the null hypothesis H0 can be written as mu1 minus mu2 equals k. Since mu1 minus mu2 is called the hypothesized mean difference, the null hypothesis can be seen as hypothesized mean difference being equal to k. This form of the null hypothesis can be used to test the hypothesis using the confidence interval for the difference of the two means. If k is inside, we accept the null. Otherwise, we reject the null. All right, we can now discuss the details of the testing procedures for these two forms of the hypothesis. We have seen three methods of testing: the confidence interval method, the test statistic critical value method, and the p-value method. We will discuss all of these for the basic form. In fact, you are required to know all three methods of testing procedures for the basic form of hypothesis. I will briefly discuss the three methods for testing the advanced form of hypothesis as well. However, if you learn and remember how to construct the confidence interval and test the advanced form, that should suffice for this class. Okay, before looking at the equations for the confidence intervals, test statistics, and also the p-values, we will briefly look at the theories used in obtaining those equations. We are still using the central limit theorem, but this time we have two populations. So we will need a little bit of more generalized background. To see this stuff, we will let x1 be a random variable which follows a normal distribution with a mean of mu1 and a variance of sigma 1 squared. We will let x2 be another random variable which also follows a normal distribution with a mean of mu2 and a variance of sigma 2 squared. Then x1 minus x2 will also follow a normal distribution. Their normal distribution will have a mean of mu1 minus mu2, which is immediately intuitive. The variance is sigma 1 squared plus sigma 2 squared. Well, the variance is also intuitive because we are pooling two random variables, even though we took the difference, meaning the variance should be more in the pooled data. However, if you would like to not too immediately accept the variance being added up rather than being subtracted, then I suggest that you try a simple MS Excel based simulation. You already know how to generate random numbers from the normal distribution using MS Excel random number generator. Generate about 25,000 random numbers from a normal distribution, say with a mean of 100 and a standard deviation of 3, which means the variance is 9. Generate another 25,000 random numbers from a normal distribution, say with a mean of 70 and a standard deviation of 4, which means the variance is 16. Then subtract the second set of generated random numbers from the first set. Draw a histogram for the resulting data. You will see a symmetric bell curve. Calculate the mean and the variance for the generated data. You will see that the mean is approximately equal to 30 if you use the numbers that I suggested. That's because the first random variable had a mean of 100 and the second random variable had a mean of 70. Then 100 minus 70 equals 30. The variance, however, will be 25. That's because the first variable had a variance of 9 and the second variable had a variance of 16. All right, that should help you understand the distribution of x1 minus x2. All right, similarly, x1 minus x2 minus k will also follow a normal distribution with a mean of mu1 minus mu2 minus k and a variance of sigma 1 squared plus sigma 2 squared. Adding or subtracting a constant from the normal distribution does not affect its variability. You can see it with a similar simulation if you like. All right, then look at the same x1 and x2 defined above. If we take samples of size n1 from the random variable x1 and calculate the sample mean x1 bar, then from the central limit theorem, we have x1 bar follows a normal distribution with a mean of mu1 and a variance of sigma 1 squared divided by n1. Similarly, if we take samples of size n2 from the random variable x2 and calculate the sample mean x2 bar, then from the central limit theorem, we have x2 bar follows a normal distribution with a mean of mu2 and a variance of sigma 2 squared divided by n2. Then what should be the distribution of x1 bar minus x2 bar? According to what we saw earlier, x1 bar minus x2 bar should follow a normal distribution with a mean of mu1 minus mu2 and a variance of sigma 1 squared over n1 plus sigma 2 squared over n2. Similarly, what should be the distribution of x1 bar minus x2 bar minus k? x1 bar minus x2 bar minus k must also follow a normal distribution with a mean of mu1 minus mu2 minus k and a variance of sigma 1 squared over n1 plus sigma 2 squared over n2. All right, we can quite easily combine these and derive the confidence interval and the test statistic exactly like how we derived them for the z-test and the t-test. I'm not planning to show all the steps, but when you have these distributions, if you also remember the z-score calculation and the derivation of the z-confidence interval and the z-test statistic, as well as extending to the t-confidence interval and the t-test statistics from the previous lectures, then you can easily derive the equations yourself. I will give you only the final equations because the derivations are not too important for this class. All right, let's look at the test procedures for the basic form, where the null hypothesis H0 is mu1 equals mu2, or equivalently, mu1 minus mu2 equals 0. We have all three testing procedures. We may do a 100 minus alpha% confidence interval, or calculate the test statistic, or check the p-value. It's easy to understand the three testing procedures for the basic form. Just to recall you again, we assume that the null hypothesis holds true and then build these tests. Then we see if certain conditions are being met so that the assumption of the null hypothesis can be either accepted or rejected. All right, let's look at these methods one by one. The confidence interval method is as easy as always. If we know the two standard deviations, sigma 1 and sigma 2, of the two independent populations, then we go for the z confidence interval. Because there are two means involved, we find a z confidence interval for the difference of two means. Based on the alternative hypothesis of the basic form, we may need a two-sided, left-sided or right-sided confidence interval for the difference of the two means. Here is the equation for the two-sided z confidence interval for the difference of the two means. It looks somewhat complicated, but the stuff should be making sense. x1 bar is the mean of the sample taken from population 1. x2 bar is the mean of the sample taken from the population 2. z half alpha is the two-sided z critical value, which is 1.96 if the confidence interval is 95%. And sigma 1 squared is the variance of population 1. Sigma 2 squared is the variance of population 2. N1 is the size of the sample taken from population 1. And N2 is the size of the sample taken from population 2. You can directly use the calculator TI-84 to construct this confidence interval. Therefore, you do not have to remember this equation. You will need this two-sided z confidence interval if your alternative hypothesis is a two-sided alternative, i.e. your H1 should be mu1 not equal to mu2. All you have to do is to see if 0 is inside of the confidence interval. If it does, you accept the null hypothesis, which indicates the true mean difference is equal to 0. If 0 is not inside of the confidence interval, then we reject the null hypothesis, i.e. the data support the alternative hypothesis, which indicates the true mean difference is not equal to 0. Remember again, this confidence interval is for the difference of the two means. Alright, if your alternative is right-sided, i.e. if H1 is of the form mu1 is greater than mu2, then you will need an upper confidence interval. Once again, the testing procedure stays the same. See if 0 is inside of the confidence interval. If it does, accept the null hypothesis. Otherwise, reject the null hypothesis. Similarly, if your alternative is left-sided, i.e. if H1 is of the form mu1 is smaller than mu2, then you will need a lower confidence interval. Testing procedure stays the same. See if 0 is inside of the confidence interval. If it does, accept the null hypothesis. Otherwise, reject the null hypothesis. Alright, that's it about the Z confidence interval method. As you saw, the Z confidence intervals require sigma 1 and sigma 2. In case if we don't know them, we have to use the sample estimated standard deviations S1 and S2. In such cases, you have to go for the T confidence intervals. I will quickly show you the equations. The test procedure stays the same. All you have to do is to see if 0 is inside of the confidence interval, because the confidence interval is for the difference of the two means. If 0 is inside of the confidence interval, then accept the null hypothesis at 0. If 0 is not inside the confidence interval, then reject the null hypothesis at 0. Here is the equation for the two-sided T confidence interval. Once again, you do not have to remember this equation either, since the calculator has an inbuilt function for the T confidence interval as well. Here is the equation for the lower T confidence interval, and here is the equation for the upper T confidence interval. Alright, we are done with the confidence interval method. We saw both Z confidence intervals and T confidence intervals. Let's look at the test statistic approach. If both sigma 1 and sigma 2, which are the population standard deviations for populations 1 and 2 respectively, are known, then we go for the Z-test statistic. This is the equation of the Z-test statistic under the basic form of the null hypothesis, where the hypothesized mean difference is equal to 0. If we don't know sigma 1 and sigma 2, then we use the sample estimated S1 and S2 and calculate the t-test statistic, which is given on the screen. The t-test statistic will also need the degrees of freedom. Exact degrees of freedom is given by this equation. Since it's complicated, some people also use an approximation, which is taking the minimum of n1 minus 1 and n2 minus 1. But we don't need the complicated equation as well as the approximation, because the calculator output has the degrees of freedom. If your calculator gives a decimal number as the degrees of freedom, then round it to the nearest integer. For the critical value, you will have to use this degrees of freedom with the distribution inverse t, and the calculator may give you an error message if decimals are entered as degrees of freedom. Testing procedures with the test statistics stay the same. For Z-test statistic, you will have to compare against the Z critical values. For T-test statistics, you will have to compare against the T critical values. The p-value method is also the same. The p-value for a left-sided alternative is the area to the left from the test statistic. For a right-sided alternative, the p-value is the area to the right from the test statistic. And for a two-sided alternative, the p-value is the area to the left from the negative test statistic plus the area to the right from the positive test statistic. Testing procedure based on the p-value stays the same. You reject the null hypothesis if the p-value is lesser than alpha. You accept the null hypothesis if the p-value is greater than alpha. Please also note that rejecting or accepting the null hypothesis is not the final step. After that step, every time you have to interpret the test result with respect to the alternative hypothesis. Alright, we will see a couple of examples. Alright, here's an example. A product developer is interested in reducing the drying time of a primer paint. Two formulations of the paint are tested. Formulation 1 has a new drying ingredient that should reduce the drying time. And formulation 2 is the standard chemistry. From experience, it's known that the true standard deviation of drying time is 8 minutes. And this inherent variable should be unaffected by the addition of the new ingredient, i.e. sigma 1 equals sigma 2 equals 8. 10 specimens are painted with formulation 1 and another 10 specimens are painted with formulation 2. The two sample average drying times are x1 bar equals 112 minutes and x2 bar equals 121 minutes respectively. Alright, the first question is, write down the null and the alternative hypothesis to be tested. We will let mu1 and mu2 be the true mean drying times for formulations 1 and 2 respectively. This is the step of defining mu1 and mu2. This step is required. The null hypothesis H0 is mu1 equals mu2. The keyword underlined is reducing. Therefore, if the new ingredient reduces the drying time of formulation 1 must be shorter because it's the formulation 1 which contains the new ingredient. So the alternative hypothesis H1 should be mu1 is lesser than mu2, i.e. this is a left-sided test. Next question. What's the appropriate statistical test? Explain. For this question, sigma 1 and sigma 2 are given, and the two samples must be considered independent. Therefore, the test is a two-sample z-test. You must also explain why it's a two-sample z-test. Therefore, write the explanation. Two independent samples with known standard deviations. Next question. Test the hypothesis using the test statistic critical value method. Use alpha equals 5%. Interpret the test result. This is a left-sided test. Therefore, the complete alpha is kept on the left tail of the standard normal distribution, and we get negative 1.645, or you can just say negative 1.65 as the left critical point. Therefore, the rejection region is from negative infinity to negative 1.65. The test statistic can be found as negative 2.5156. Let's go to the calculator and find it. Alright, here's the calculator. We don't have a data set. The statistics are given. Therefore, we can straight away go ahead and run the two-sample z-test. Go to Stat and then select Tests. And then if you go down, you can see that number 3 is two-sample z-test. Select number 3, two-sample z-test. Hit enter. And then we have to define the input method. For this question, we don't have a data set. Select Stats and then hit enter. Now you can define sigma 1, sigma 2, x1 bar, n1, x2 bar, and n2. Those must be read from the question given. Sigma 1 is given as 8. Sigma 2 is also equal to 8. x1 bar is given as 112. n1 is 10. x2 bar is given as 121. n2 is also equal to 10. And then we have to select the correct alternative. This is a left-sided test. Therefore, select mu1 is lesser than mu2, the one in the middle. After selecting the test, make sure to hit enter. If you do not correctly select the alternative, your p-value will be affected. Skip color and then select calculate and then hit enter. Here is the calculator's output for the two-sample z-test procedure. Always start by reading the first line of the calculator's output. It should indicate your alternative hypothesis. First line says mu1 is lesser than mu2, which exactly is what we have as the alternative hypothesis. Therefore, we can go ahead and use rest of the output of this calculator. Alright, therefore the test statistic is negative 2.5156, which is clearly in the rejection region. Therefore, we reject the null hypothesis. Now we must interpret the test result. We rejected the null hypothesis. This means the data support the alternative hypothesis. And as always, we must interpret the fate of the alternative hypothesis. Therefore, the interpretation should be: we have statistical evidence with 95% probability to conclude that the new ingredient reduces drying time. Alright, the next question is, what's the p-value of the test? Test the hypothesis using the p-value. Do you get the same answer? The p-value is also given in the same calculator output, the third line. The p-value is 0.0059, which is clearly lesser than 0.05. Therefore, also, we reject the null hypothesis H0. Once again, we get the same conclusion. We do not have to write down the interpretation again, because the interpretation also stays the same. Then, the next question. Construct a 95% confidence interval for the true mean difference of drying times. Test the hypothesis using the confidence interval. Do you get the same answer? Okay, let's go to the calculator again. This is a left-sided test. Therefore, we need a 95% lower z confidence interval. Since the calculator does only two-sided z confidence intervals, we will do a 90% two-sided z confidence interval for the difference of the two means. Let's go to the calculator. First, you have to go to Stat, and then select Tests. And then if you go down, you can see number 9, two-sample z interval. Select number 9, two-sample z interval. Hit Enter. Now you have to define the input method. Once again, the input method is statistics. Select that and then hit Enter. And then we have to define sigma 1, sigma 2, x1 bar, n1, x2 bar, and n2. They are automatically imported from the previous calculation of the two-sample z-test. Therefore, I do not have to enter them once again. I have to change the confidence level from 0.95, the default value, to 0.90. Select Calculate and then hit Enter. So the 90% two-sided z confidence interval for the difference of the two means is from negative 14.88 to negative 3.115. Therefore, the 95% lower z confidence interval for the difference of the two means is from negative infinity to negative 3.115. This is a question of the basic form, which says the hypothesized mean difference is equal to 0. So we have to see if 0 is inside of the confidence interval, which is constructed for the hypothesized mean difference. Clearly, 0 is not inside the confidence interval. Therefore, we reject the null hypothesis. Once again, we get the same conclusion. So we don't have to write the interpretation again. Alright, I'm not planning to do another examples from right-sided and two-sided tests. Those are similar to the example discussed. If you don't remember the rejection regions and the critical values for two-sided and right-sided z-tests, you may have to watch the z-test video again. This example is from the two-sample t-test. Let's go ahead and read. Arsenic concentration in public drinking water is a potential health risk. An article in the Arizona Republic, May 27, 2001, reported drinking water arsenic concentrations in parts per billion for 10 metropolitan Phoenix, population 1 communities and 10 communities in rural Arizona, which is population 2. The sample statistics are x1 bar equals 12.5, s1 equals 7.63, and x2 bar equals 27.5, and s2 equals 15.3. Test if there is any difference of the true mean arsenic concentrations between metro and rural areas. The first question is, write down the null and the alternative hypothesis to be tested. We will let mu1 and mu2 be the true mean arsenic levels in metro and rural. According to the keyword underlined, difference, we have to see if there is any difference between the two means. The null hypothesis H0 is mu1 equals mu2. The alternative hypothesis H1 is mu1 is not equal to mu2. All right, the next question. What's the appropriate statistical test? Explain. For this one, we have to do a two-sample t-test because we have two independent populations and the population standard deviations, sigma 1 and sigma 2, are not given. Next question. Test the hypothesis using the test statistic critical value method. Use alpha equals 5%. Interpret the test result. All right, let's go to the calculator and run the two-sample t-test procedure. There's no dataset given once again. We have the statistics. Therefore, we can straight away go ahead and run the two-sample t-test. Go to Stats, select Tests, and then you have to select number 4, two-sample t-test. Select number 4, two-sample t-test, and then hit Enter. Input method is once again statistics, not data. Select Stats and then hit Enter. Now you have to define x1 bar, sx1, n1, x2 bar, sx2, and n2. For this question, x1 bar is 12.5. sx1 is the standard deviation for the population 1, which is given as S1, which is 7.63. N1 is 10. X2 bar is 27.5. Sx2, which is given as S2, is equal to 15.3. N2 is also equal to 10. And then the alternative hypothesis. This is a two-sided test of the form mu1 is not equal to mu2. Select that and then hit Enter. And next line is pooled, no or yes. It's always no. We give pooled yes if the two variances from the two populations are given as equal. In that case, the equation becomes somewhat simpler. But we don't have to worry about how complicated the equations used. Therefore, select pooled as no always. Hit Enter. And then skip color and then select calculate and then hit Enter. As always with the calculator output, make sure to check the first line of the output. The first line is mu1 is not equal to mu2, which exactly is what we have under our alternative hypothesis. Therefore, we can go ahead and use the rest of the output. The second line indicates the test statistic. So the test statistic is -2.774. And according to the output, the degrees of freedom is 13.215, which is approximately 13. Remember always that the degrees of freedom should be rounded to the nearest integer. Otherwise, you will get an error message when trying to find the critical values using the inverse t function. This is a two-sided test. Then what should be the rejection region? You keep half of alpha, which is 0.025 on each tail of the t distribution with 13 degrees of freedom, and then read the critical value. You have to go to distribution and select number 4 inverse t. Then you will see that the two critical values are -2.16 and +2.16. Therefore, the two rejection regions are from -infinity up to -2.16 and from +2.16 up to +infinity. The test statistic -2.774 is on the rejection region. Therefore, we reject the null hypothesis. Rejecting the null hypothesis means the data support the alternative hypothesis. So we have to interpret it as that. We write the interpretation explaining what happens to the alternative hypothesis. So the interpretation is we have statistical evidence at alpha equals 5%, or you may also say with 95% probability to conclude that the true mean arsenic levels differ. The next question, what's the p-value? Test the hypothesis using the p-value. Do you get the same answer? According to the calculator output, the third line indicates the p-value, which is 0.01558, which is lesser than 0.05. Therefore, also, we reject the null hypothesis. This also gives us the same answer. Interpretation is also the same. The next question. Construct a 95% confidence interval for the true mean difference of arsenic concentrations. Test the hypothesis using the confidence interval. Do you get the same answer? Since this is a two-sided test, we will need a two-sided T confidence interval. Let's go to the calculator. We have to go to Stat, select Tests, and then you have to go down and select two-sample T interval, which is number 0. Number 0, two-sample T interval. Select that and then hit Enter. Input method is statistics. Select Stats and then hit Enter. Then you have to define the given statistics. Since we already ran the two-sample t-test procedure, they are all imported automatically, so I do not have to re-enter. The confidence level this time should stay as 0.95. Once again, pooled should always be no. Select Calculate and then hit Enter. Alright, the two-sided 95% T confidence interval is from negative 26.66 to negative 3.339. This is also a hypothesis given on the basic form. We have to see if 0 is inside of the confidence interval. Clearly, 0 is not inside of the confidence interval. Therefore, we reject the null hypothesis. Once again, we get the same conclusion. Interpretation does not have to be written again, since we already wrote it earlier. Alright, the last two examples we did were based on statistics. Sometimes you may also get the dataset. If so, you have to first enter the dataset and run the appropriate statistical test procedure. It will be equally important to know how to run the tests when the data are given instead of the statistics. Here is the dataset for this same question. Please try the question with the dataset instead of the given statistics and see if you can still get the same answers. All right, I think at this point you have a good understanding on the basic form of hypothesis. We will also briefly see the theories behind the advanced form of the two-sample tests. Under advanced form, you can write the null hypothesis H0 as mu1 minus mu2 minus k equals 0. You may also write k on the right-hand side. If so, it's easy to see k is the hypothesized mean difference. The reason the null hypothesis is written this way is because that form of the null hypothesis is used for deriving the test statistic and the confidence interval. Because we assume that the null hypothesis holds true when deriving those equations. Alright, we have all three methods: the confidence interval, the test statistic critical value, and the p-value method. First, we will see the confidence interval method. You will have to test the hypothesis of this form using the confidence interval method in the exams. The method is very easy. The equations for the left-sided, two-sided, and the right-sided confidence intervals are the same equations for the difference of the two means. All you have to do is to see if k, the hypothesized mean difference, is inside of the confidence interval. If it does, we accept the null hypothesis H0. If not, the null hypothesis H0 should be rejected. The findings should be interpreted in the context of the problem given. Second, the test statistic critical value method. I will not hold you responsible for using this method. The reason is there is no direct calculator shortcut for this method. However, you can easily modify the calculator dataset by subtracting k from the second dataset and writing the equation accordingly. I will let you think about the rest of it. The equation for the test statistic will be modified. For known sigma 1 and sigma 2, the z statistic is given here. For unknown sigma 1 and sigma 2, we have to use the sample standard deviations S1 and S2 and obtain a t-test statistic. Except the equations of the test statistics, the test procedures i.e. comparison with the critical values, stay the same. The next method is the p-value. The test procedure stays the same here as well, i.e. if the p-value is lesser than alpha, then you reject the null hypothesis. If not, you accept the null hypothesis. Interpretations should follow. Once again, out of all three methods, you must properly know how to use the confidence interval method. You can easily use MS Excel for the test statistic method, if you like. It gives you a place to enter the hypothesized mean difference so that you do not have to modify the given data set. It will also give you the p-value. However, as mentioned earlier, the test statistic and the p-value methods for advanced form of hypothesis for two mean comparisons are optional for this class. Let's do an example with the confidence interval method. Randomly selected average temperature readings during the month of March 2021 for Kansas City, Kansas and Houston, Texas are given below. Construct a 95% upper confidence interval and see if there is statistical evidence to support that the true average temperature in Houston is part A 15 degrees and part B 20 degrees, higher than the true average temperature of Kansas City during the month of March. All right, the dataset is given. Clearly, we have two independent datasets. We will let mu1 be the true mean of Houston temperature during March. We will let mu2 be the true mean of Kansas City temperature during March. We will do a confidence interval for the mean difference, mu1 minus mu2. For part A, we have to see if Houston temperature is 15 degrees higher. And for part B, we have to see if Houston temperature is 20 degrees higher. For both cases, we will need right-sided tests. So we will first construct a 90% two-sided t-confidence interval using the calculator. All right, here's the calculator. Since the dataset is given, we have to first enter the given dataset. I will go to Stat, select Edit, number 1, Edit, hit Enter, and I'm going to enter Houston temperatures into the list L1, Kansas City temperatures into the list L2. So the first observation is 61. The second observation is 62. The third observation is also equal to 62. All right, I will pause the video now, enter the complete dataset and come back. All right, I entered the complete dataset. Now we have to construct a 90% two-sided t-confidence interval for the difference of the two means. I will go to Stat, select Tests, and then you have to go down until you see two-sample t-interval. Select number 0, two-sample t-interval. Remember again, there are two places that you will see t-interval. It is not the number 8 t-interval. Number 8 t-interval is only for single population mean. Since we are constructing a confidence interval for the difference of two means, select number 0, two-sample t-interval, and then hit Enter. Now we have to define the input method. Input method is data. Select data and then hit Enter. List 1 is L1. List 2 is L2. Frequency 1 is 1. Frequency 2 is also equal to 1. The confidence level, this time is a 0.90 confidence level is what we need. Pooled is always no. Select Calculate and then hit Enter. All right, therefore, the 90% two-sided t-confidence interval for the average temperature difference is from 19.822 to 22.456. This means the 95% upper t-confidence interval for the average temperature difference is from 19.822 to positive infinity. For part A, we have to see if the temperature difference is greater than 15. This means the null hypothesis, hypothesized mean difference, mu1 minus mu2 is equal to 15. The alternative hypothesis is the hypothesized mean difference is greater than 15. Therefore, we have to see if 15 is inside of the confidence interval. No, 15 is not inside. Therefore, we reject the null hypothesis H0. This means the data support the alternative hypothesis. i.e., the interpretation is we have statistical evidence with 95% probability to conclude that the true average temperature of Houston, Texas is more than 15 degrees higher than the true average temperature of Kansas City. All right, next for part B, we have to see if the temperature difference is greater than 20. This means the null hypothesis is hypothesized mean difference, mu1 minus mu2 equals 20. The alternative hypothesis is the hypothesized mean difference is greater than 20. We have to see if 20 is inside of the confidence interval. Yes, 20 is inside of the confidence interval, i.e., we accept the null hypothesis. Accepting the null hypothesis means the data do not support the alternative, i.e., the interpretation is we have no statistical evidence with 95% probability to conclude that the true average temperature of Houston is more than 20 degrees higher than the true average temperature of Kansas City. All right, that's basically it I need to discuss for the class of today. Thanks for your class participation. Have a nice day.